So maybe first start off by framing how does Broadcom sort of look at the requirements for a scale-out data center? What are the key things from the switching technology that need to be delivered? At a high level, it needs to be basically solve the N by M connectivity problem between server and storage endpoints. Be able to provide that massive scale-out capability. Provide it in a highly reliable, highly available, high throughput framework. Be able to scale that up in addition to scale that out, meaning generationally be able to deliver constant increases in bandwidth, in efficiency of that bandwidth per unit of cost, as well as per unit of power. That's fundamentally what drives the OpEx for scale-out data centers, at least on the networking component, to be truly world-class. And then fundamentally, to get out of the way. If you look at it from the standpoint of the server application developer, the network needs to be opaque. We don't want server application developers to have to be intimately aware of everything that's going on with the network. From the network engineering side, you need the network to be transparent and highly malleable, highly provisionable, and to be able to provide the performance that's required for all the applications that are running on that infrastructure. So Broadcom's latest solution for this class of applications, the scale-out data center network, is Tomahawk 3. Tomahawk 3 was announced and sampled late last year. It is a 12.8 terabit per second switch chip, multi-layer switch chip. Just to give you some index on that, 12.8 terabits per second used to be the total amount of switching bandwidth you would find in a 8 or 16 slot chassis, maybe just a few years ago. All of that is now integrated on a single piece of silicon with Tomahawk 3. Tomahawk 3 supports not just existing 100 gig links, but also using 56 gig PAM4 signaling can support the next generation of cloud scale interconnect, 200 gig and 400 gig interconnect for the next build out of leaf spine networks. So Tomahawk 3 provides effectively monster bandwidth, the highest amount of bandwidth integration on a single piece of silicon to date. Leading edge speeds and feeds in terms of supporting any port speed configuration ranging from 10 gig all the way to 400 gig. It is specifically architected for hyperscale. It's architected to solve the problem that we talked about on the first slide, which is be able to provide scale-out connectivity that's robust, reliable, allows for very wide ECMP scale for load balancing, allows the telemetry that is required in order to monitor and operationalize the network. And as I mentioned, by pushing up this bandwidth curve, you basically scale the network to be able to deliver the best CapEx and OpEx at a given generation. And that's fundamentally critical when you're thinking about the scale-out model. Every network operator has to go through a TCO calculation of how much capital to outlay and what kind of expense when it comes to power of the network, the optical links in the network, the cabling. All of these pieces add up to your total cost of ownership of that network in a given generation. So making the decision to migrate from, for example, a 3.2 terabit per second switching element to 6.4 or 12.8 requires you to cull all those inputs and to figure out how much more efficient the network can really be. So it's not just about blasting more bandwidth, it's about a TCO calculation where your CapEx and OpEx for operating the network is significantly reduced when you go to this next performance node. And then lastly, high velocity deployment. So our track record at Broadcom has been in delivering a new generation and effectively doubling the performance of the switching element once every 18 months, roughly. And we do that across multiple different architectures. For the hyperscale and scale-out cloud market, we've done that with the Tomahawk family for several generations now. And that's what's illustrated on this slide. In terms of you look at the procession going all the way back to 2010 when the first generation Trident device at 640 gigabits per second was released. In a matter of 7 years, we've multiplied that bandwidth 20x. So that's greater than the performance gains that Moore's Law would otherwise deliver. And how do we do that? And what's driving that? the first thing that's driving that is definitely the demand from the application side. Cloud scale applications now, deep learning being implemented using specialized compute accelerators or alternative computing nodes, as well as the disaggregation of storage, so the separation of compute and storage and being able to carry that over effectively Ethernet links. That's multiplying up the requirement at the edges of the network, at the endpoints of the network for bandwidth. That's, in addition, driving the requirement for more bandwidth in the layers above that, the leaf, spine, superspine layers that exist in the network above that. And then how do you actually solve the problem of scaling performance from generation to generation? Well, to do that fast, what Broadcom did was basically focused on power reduction, reducing power per port by 40% in the Tomahawk 3 generation. Being able to also have a highly scalable architecture that allows you to scale not just the bandwidth, but the buffering, the table scales, the amount of capacity that the switch overall needs, the telemetry to be able to move from a particular bandwidth node to 2x in a short amount of time. And to do that in a ultra-efficient design in 16-nanometer silicon technology. Those are the keys that really led to Tomahawk 3 being available, and to be launching the market into this next wave of build-outs that are possible at 100, 200, and 400 gig. In terms of what it takes to actually build this type of scalable architecture, there are really three components when you think of a switch chip. Switch chip is composed of a memory management buffer unit, a set of pipelines that do the packet processing, and the SerDes I/O that integrates around the perimeter to actually pull in and ingress and egress all of the traffic. For each of these, there needs to be a very specific bent towards scalable design in order to be able to quickly move generationally up the bandwidth curve. And that's what are the key components and key attributes of the Tomahawk architecture. It's highly scalable in terms of buffering, a shared buffer architecture that allows you to integrate support for very high burst absorption, congestion control, and be able to ensure that you effectively have extremely little loss in the network when going through these switch elements. A scalable pipeline. There's a lot of debate right now in the market as to whether a pipeline should be scalable or programmable. Fundamentally, we believe that to solve the cloud scale interconnect problem, to be able to do that repeatedly and to do that efficiently, you need a lightweight pipeline, one that can actually scale to a very high pipeline count in order to scale up your performance, and that has very, very efficient memory and digital design elements. From the I/O side, moving from 25 gig NRZ to 50 gig PAM4 is an important lift from a signaling point of view. For those of you who don't know, existing 100 gig links are built on 4 lanes of 25 gig non-return to zero signaling, or NRZ. And that is now moving to 50 gig PAM4 signaling, which is 4 levels of amplitude modulation to be able to encode more bits. And the new Ethernet speeds at 200 gig and 400 gig, both on the electrical and optical side, are based on PAM4 technology. And being able to implement that and have design control of that IP to be able to replicate it 256 times on the same chip and be able to do that in a low power envelope, that's key to being able to scale a switching solution to these extremely high bandwidths that are required by the network. So what does this architecture provide? What, as a designer of data center infrastructure, care about? Well, care about a few things. First of all, efficiency of design. Fundamentally, by moving up the bandwidth curve, it's not just about fatter links, it's also about efficiency of the network. How many layers of the network it takes, or how much total switching outlay you need in order to connect n number of endpoints. For a 5K server endpoint class network, moving from a 6.4 terabit per second solution to a 12.8 terabit switching element saves you 50% of the structured optical cabling. 50% reduction. You cut it in half, the number of optical links you need. You cut the latency by 60% because you're moving from what could be a multi-hop network into basically a single stage. 400 nanoseconds nominal port to port. And third, you reduce the network power. The network power can be collapsed as much as 75% in that example because you're using fewer switching elements, and each of those switching elements are reducing power per port by about 40%. So the reasons to upgrade the network at this cadence are clear. The issue is ensuring that you have an architecture at the aggregation layers that allow you to move fast in terms of adopting that, and the overall technology ecosystem from the optics point of view, from the hardware platform point of view, to be able to deliver those solutions in a timely manner. And that's what we're able to actually do here with this Open19 project, having the switching element with Tomahawk 3 be a featured element of that solution, but also the ability to integrate optics and a virtual network topology that allows you to collapse what was previously very big iron, very expensive gear that integrated multiple switch chips and complex chassis designs into a very standard, hardware-efficient form factor featuring a single switch chip with Tomahawk 3 at the center of it. And with that, I'll give it to Rob.
Okay. Good afternoon, everyone. So my name is Rob Stone. Oh, sorry. Changing the programming. There you go.
That's okay. Hi, I'm back. So we've seen this picture before. It doesn't look a lot different. My interaction with this next generation concept is what are we going to do with the external cable when we need to go to the faster solutions on the inside, and when you hear about what Rob has to talk about next. But essentially, the concept that we've been playing with is what does it look like to add standard fiber-based solution into the same back shell and into the same spine. So we have a lot of tools in our toolbox that we can play with. We currently do a lot of routed ribbon flex planes. We do ribbonizing of the cable. If you've stopped over, you can see that we've done a concept and mock-up with what a standard fiber solution would look like inside the spine. It works, and you won't have to change out your hardware. So that's pretty much it for me. I'm sure you're more interested in what Rob has to say about Kobo.
Okay, thank you. Okay, so my name is Rob Stone. I'm part of the Broadcom switching team. But today I'm going to be wearing a different hat. I'm going to be talking to you about Kobo. I'm a board member for Kobo. Those of you who do not know what Kobo is, let me explain. So Kobo is an industry-driven organization. We have about 70 members to date, and we were formed about 3 years ago to develop a common form factor for a mid-board optical module. So you may be familiar with things like SFPs and QSFPs, which are typically front panel pluggable modules. Well, this is a little different to that in that we're taking the optics and we're putting it onto the board, which enables some interesting new attributes, which I'll go into in a bit further in this presentation. But just to give you a quick idea of the different Kobo form factors which we have standardized, we've got two main varieties. One's an 8-lane version, so 8 electrical lanes, and the other one's a 16 electrical lane version. And as you can see in the slide right here, there are 3 different sizes associated with the 8-lane and 16 lane. And to a high level, those are associated with different power dissipation classes. So the idea here is we can put everything from short-reach optics to very long-reach optics like coherent modules that might get used in intra-data center and inter-data center communications and put them all into the same socket. So that's the basic general idea behind Kobo. So operational benefits from doing that. So first of all, you can deploy a switch with everything pre-cabled. All the optical modules are pre-installed at the factory before it ships to your data center. And so your time to turn up and go live is very much improved to if you have to individually unbox all your optical modules and plug them all in on the front panel. Some of them maybe won't seat properly. And operationally, people have seen challenges with that. Secondly, because these are pre-installed and pre-tested, the thermal and signal integrity for this is better. You have a reduced failure rate. You can potentially locate those optical modules closer to the source. So in this, for a switch application, it will be closer to that switch chip. And so you can potentially get to lower power consumption because those electrical channels are easier because they're just shorter. There's less touching. And so as we all know, people try to strive for this zero-touch networking kind of paradigm, so less human interaction, so decreased failures with that. And then importantly here, relative to Open 19 is Kobo optical modules will support both front panel and backplane blind mate optical connectivity. And so this really enables a good optical backplane connection, which is something that you can't obviously do with a front panel pluggable module where you're plugging the fiber in individually into the modules. So just talk a little bit about the future for Kobo. So Kobo was originally developed with 25 gig and 50 gig signaling. This was some work that was done by TE Connectivity, who's one of the participants in Kobo who's responsible for the high-speed electrical connector. And here, this data is showing that really Kobo's future-proofed to go to 100 gig per electrical lane. So as Rochan mentioned in his lightning talk, we're kind of seeing the speeds, the electrical I/O speeds from switching kind of march forward from 25 gig NRZ, which is deployed today, to 50 gig PAM4, which will be the Tomahawk 3 generation. And then in the future, when we run out of bandwidth, we'll have to go to 100 gig PAM4. Well, this is encouraging for us that we'll have the optical connectivity that has modules with the right electrical connectivity of 100 gig per electrical lane. So Kobo is future-proofed to 100 gig per electrical lane. That's the kind of takeaway from this slide right here. So this slide's kind of a little bit of an eye chart, but I think it's worth kind of pointing out and walking through this a little bit slower, because this really talks to you about the application space for Kobo-based optical modules as opposed to what you might see with the other front panel pluggables like QSFP, QSFP-DD, and OSFP. And so as you look, so what the first couple of lines in this chart right here, what I'm showing is if you were to build a 1RU pizza box, or a box with 1RU front panel I/O. If you wanted to build it with a QSFP, you can certainly enable a 3.2T or a 6.4T switch. If you want to go higher in bandwidth than that, then typically you're forced to, for front panel connectivity, you're forced to solutions like QSFP, DD, and OSFP, which should carry you all the way, certainly to 25.6. But then there's some questions about whether or not they'll continue to scale past that point, just because that would force you to go to greater than 100 gig per lane on the electrical connector. But if you look on the very far right-hand side, because Kobo's not space limited on the front panel, and we have the flexibility to put the modules actually on the board, Kobo can scale all the way from 12.8T all the way through greater than 25.6T of switching. So it's a flexible solution. It gives you another degree of freedom in your system design. So that's kind of on the kind of raw bandwidth side of things. We talked about the fact that Kobo will also support a blind mate optical backplane. There are downsides to using a midboard optic, which I should point out. So it's not field serviceable, right? So once you've installed these things, you can't easily touch them. You'd have to take the rack out. It's really kind of something that needs to be done in a semi-clean environment to service those optics if they're in the midboard. And also, Kobo's is dedicated for optics only. It doesn't support direct attach copper cables. So unlike the front panel pluggables where you can have a DAC option, that wasn't part of the design intent for Kobo, and so it doesn't support that. And secondly, as we talked about, it enables you to do flexible board placing and also maybe better heat sinking because you're not packing these modules on top of one another and getting a very dense thermal environment in your front panel with restricted airflow. So again, when you really were trying to push the bandwidth limits to really the very bleeding edge, then Kobo may give you another degree of freedom to solve those problems. So I think that's pretty much it. Thank you.
So now that we have a 12-8 switch, and we have an optical interconnect, and we have an onboard optics, and we have the cages of the Open 19, which has been already developed, and like Liz said, the optical connection system actually will fit the same form factor, so you don't have to change anything. You can use the same power cables. You move to an optical cable, and what can we do with that? So we look at this, and we say, okay, if you take a non-blocking environment and you stack, instead of full-width servers, switches. We take like a white box 1RU switch design, and we stack it together with an optical shelf in the middle. What can we do with that? The easiest thing to do with that is create what we call a cloth in a box. But it's not in a box. This time it's going to be a cloth in a cage. We're going to take all those subcomponents, connect them together, create two types of components. Components which will sit with front-end ports, components which will go with back-end aggregation layer. And by that, can create an enormous switch in the configuration. In the solution of the optical cable back connection, we can go up to 24 fibers for every one of those building blocks and aggregate it into a large connector into the optical shelf. So if we take that and say, OK, let's build a front slice, which has 16 ports of QSFP-DD, which aggregates into 6.4 terabit on the front. And to make it non-blocking with the Tomahawk in the middle, have COBO modules which are actually facing the back and connect to the optical Open19 cable, pull power from the same two connectors of power, and then by that we're creating all of our front-facing environment. If we look at the back side of that, we take a line card which actually has only COBO modules on it, no modules are facing the front, and actually aggregating the traffic through two of the Open19 optical connection. And we can create an environment which is that. We can build with 16 front slices and 8 back slices a system which is 100 terabit capable in a 26 RU, built out of 1 RU boxes into this environment, which is already predetermined, used. And we can take this to the next level when we actually build a system with the next generation chips, which will come, which is going to be 25 terabit. We'll build a 200 terabit solution. So what's the advantage in that? Why should we do that? It's going back to what Rochan said before. If you try to buy a chassis like that from one of your OEM suppliers, you will pay an unbelievable price for each and every one of those slices that we talked about. This slice or this slice is going to be extremely expensive. It's going to be probably based on a backplane connection and not on an optical backplane connection, and it has zero scalability in it. In this environment, we created scalability because it's optical interconnect. Today, we use 400 gig COBO modules. Tomorrow, we're going to use 800 or 1.6 terabit. The scale in that is actually pre-built into the system. All you need to do is get an aggregated slice, which is different, or a front-ended slice, which is different, and then create this variety of systems between 9 RU at 384 ports of 100 gig, going all the way to 24 RU with 1,100 gig connections coming off a system which is built out of a very simplistic white box environment into the Open19 cage. The power shelf stays the same, the power distribution stays the same, the cable snap-on feature connectivity, the blindment connectivity stays the same. It's all air-cooled, and you can drive this into your data center in tier 2 or tier 3 right away without making an effort and waiting for a very large OEM to build for you a very, very large lockdown solution into a 100 terabit or 200 terabit environment. The reason I'm showing this is that not that we're trying to engage a project right now, which we might. It's just to show that the platform that we defined with Open19 is so versatile, so you can even take a spin on it all the way through and say, OK, let's make out of this a switch, and it just works. It just works as a switch. All right? Thank you, guys. And if you have any questions to any one of the four of us, we'll be happy to take it. If not, we'll move to the next item. Yeah?
Operationally wise,
Yeah.
how does this compare with, let's say, the optical module failing?
Mm-hmm.
So somebody today, if the QSFP fails, okay, so you go up, you walk off to the QSFP, you unplug it,
Right.
plug in something new, off you go. This one, I have to pull out the switch
Mm-hmm.
and replace the switch.
Yeah, so the question, I'll repeat the question. The question is, from an operational perspective, how do we deal with onboard optics? And I'll let Rob comment on that as well in a second. From an operational perspective, yeah, if you are putting onboard optics, every time you have a failure on one of those optic modules, you have to pull out the card, right? What does that mean? Pull out the card means that you actually knock down 6.4 terabit worth of bandwidth out of your network connectivity. The question is, how do you build a topology? If you look at the optical box, which was in the middle over there, it enables you to build a variety of topologies on how you actually do the close in the box, or not close. You can put something else in there. The way to actually architect it properly is that even if you pull out a slice, nothing happens from a connectivity on the lower tier, because the connectivity on the lower tier is going to be sprayed across all the slices. So you can pull out a slice, and you only lose 1/16 or 1/8 of your bandwidth, but you don't lose full connectivity. And that's the beauty of building a closed environment. In general, if you do all onboard optics, I'll let Rob comment on that a little bit more, and what happens in that environment.
Yeah, so I think, I mean, to echo what you've all said, I mean, one of the ways of dealing with that is obviously at the network level, right? And the redundancy that you natively build into the network, and you build enough failover in that you can, you don't need to service a module if necessarily if it fails. That's the first issue, first attribute. And I think the second one is what we're learning and what we're hearing from both the end users and also the people that make optical modules is that, if you look at the Pareto of failures in optical modules, by a large, very large extent, most of the failures are caused by handling damage. And so if you can eliminate the handling damage, then that can be both mechanical handling damage, like chipping, pore insertion, things like that, damaging the connectors, both the electrical connectors and the optical connectors, which if anybody's familiar with optics, you'll know that that's really the bugbear of optics is dirt in the connectors. If you eliminate that by moving the optics inside the box and pre-testing it prior to shipping that from the factory, then you've really addressed a lot of the early failure mechanisms which are associated with optics.
Any other questions? I think there was a question over here. Or not. Any other questions about that? Again, if this is just an example of how can you actually break the innovation cycle? How can you actually come and say, okay, I want to do something else with this thing. And if it works or if it doesn't work, can I leverage what I'm doing with the servers? Because the number of cages and power shelves that we buy for the servers is an order of magnitude bigger than anything we're going to buy for switching. And we can leverage that cost effectiveness into our switching environment and building an extremely, extremely large networks in a relatively cost-effective way. So if there aren't any questions, thank you very much, everybody.